Hello everyone, my name is Xiaowei. It's my pleasure to attend this meeting. Now I will tell you something about our research project, the Clutter Suppression for High-Frequency Surface Wave Radar. I will introduce our research from 5 sections. Well, let's begin. As we all know, the performance of high-frequency surface wave radar degrades due to some unfavorable environmental conditions, such as ionospheric clutter, meteor trail, as well as high-intensity radio frequency interference. The detection of thin bolts, driftwoods, and other small targets faces the limitation from sea clutter, which refers to unwanted backscatter from sea surface. Sea clutter suppression is one of the major measures to improve the target detection. In Section 2, we will give you a brief introduction about some ocean clutter suppression methods. At present, the ocean clutter suppression methods can be classified into 3 categories. The first category first estimates and reconstructs the ocean clutter signal and then subtracts the reconstructed signal from original signal. The typical methods are the cycle cancellation method and neural network method. The second category first divides ocean clutter space into strong clutter subspace and weak noise subspace, and then suppresses the ocean clutter by projecting the echo signal to noise subspace. The typical methods are the eigenvalue decomposition method and singular value decomposition method. The third category first says no attenuation of signal as constraint condition and then minimize the output energy to suppress the ocean clutter. The typical method is optimal filter method. In Section 3, I will introduce the proposed framework in detail. Usually, high-frequency surface wave radar echo contains a large number of targets, sea clutter, ionospheric clutter, and interference. Therefore, the first task is asking us to accurately select the needed data, which contributes to distinguish the clutter and target in the experiment. Inspired by machine learning, we think about sea clutter estimation and suppression from perspective of semi-supervised learning. Specifically, we first select some sea clutter data that almost have no target, and the data of target coexists with sea clutter. Then we label these 2 different data and labeled training sample set for subsequent classification algorithm. With the help of dictionary learning and sparse representation, we will extract sea clutter components in radar encodes. Through the cooperation of offline training and real-time processing, this method realized improvement of clutter suppression performance and accelerate calculation speed. As the classical semi-supervised classification method, training algorithm has good performance in supervised classification, such as electronic noise learning technique and help spectral image classification. But the original training algorithm ignores the diversity of classifier types, which cannot achieve excellent classification results when number of labeled samples is limited at initial stage. In order to improve the performance of original training algorithm, the improved training algorithm with enhanced classifier diversity was proposed and has more promising results. We set the enhanced training algorithm with 4 classifiers in 2 different classes. We select 2 SVM classifiers, 2 random forest classifiers. SVM is very suitable for dealing with large input spaces and produce sparse solutions. In the classification process, SVM is based on linear modeling of classification boundary, utilizing a least squares method. Otherwise, random forest has the advantages in dealing with large-scale dataset. When the scale of dataset enlarges, the performance of random forest does not appear overfitting. Moreover, when the size of the dataset is small, random forest also has a strong generalization ability. The process of enhanced M-training is listed in detail. As for dictionary learning, in recent years, dictionary learning is a good way to acquire more knowledge and information with less resource, which is applied in various practical cases, including face recognition and classification. The goal of the dictionary learning is to learn abundant knowledge and formulate a dictionary with less content from a mass of signal training dataset. In this way, the time consumption and cost of data collection can be greatly decreased. In the training dataset, each column can contain either an original signal or features extracted from that signal. There has been a large amount of research on the dictionary learning. The process of dictionary learning is listed in detail. We propose a cooperative dictionary learning and semi-supervised learning Clutter Suppression framework to solve the clutter problem and named it CDLSL. In essence, sparse representation applies an equipped dictionary, and dictionary learning further exploits the crucial information in dictionary. Another approach, which is named semi-supervised learning, can improve the performance by applying the unlabeled samples to increase the quantity of the training samples. To complement dictionary learning and semi-supervised learning for each other, the proposed framework applies enhanced M-training algorithm with different classifiers, sparse representation, and dictionary learning to detect the targets and see clutter in high-frequency surface wave radar system. In our experiment, we will gather huge volumes of data in 6 days and then pore over it. From the figure 1, high-frequency surface wave radar encode data usually contains a large number of targets, C-clutter, ionospheric clutter, and other interference. Hence, the first task for us is to accurately select the needed data, which contributes to identify and distinguish the C-clutter and the target in the experiment. In this paper, we select the enhanced M-training algorithm. We select the C-clutter data, and the data of target coexists with C-clutter to train the 4 classifiers from ARD data. We randomly divide the entire available data in 2 parts for each class. 50% data are used for training and 50% data are used for testing. And in the training data, we randomly select 60% samples in each class as the initial labeled data, and the remaining samples are used as unlabeled data. Hence, after training the classifiers, we put the original radar data into enhanced M-training algorithm. Then, we obtain the C-clutter dataset that almost have no target. We begin to train the C-clutter frequency spectrum dictionary. Then we will obtain the C-clutter frequency spectrum dictionary and conduct the C-clutter dictionary. The above mentioned steps are conducted in quasi-real-time mode, and we represent the quasi-real-time steps in gray areas. In the traditional radar signal processing, the echo signals are received by receiving array. Then echo signals are masked, filtering, and conducted by fast filter transform. After being forming, the echo signals are directly detected by target detectors. The black arrows describe the above-mentioned procedures. Different from traditional radar signal procedure, after the being forming, the proposed algorithm makes use of dictionary to perform sparse representation of the echo and clutter suppression, and then carries out target detection on the echo signal with clutching filtering. The above-mentioned process is represented by the blue line in the Figure 1. In Section 4, we introduce related experiment results. In this experiment, we select 640 samples to train enhanced M training and obtain the oral classification accuracy between the C-clutter data and the data of target coexists with C-clutter is 77.57%. The classification results are shown in Figure 2. When we apply CDL-SL framework to summarize the C-clutter, we should utilize the earlier C-clutter data to train the dictionary, because the ever-changing weather impacts on the physical character of the C-clutter and ionospheric clutter. If we utilize the C-clutter data from a long time ago to train the dictionary, we cannot adequately mine the representative information of the current C-clutter. And the classification results of the enhanced M training algorithm are shown in Figure 3. We can reserve the C-clutter data for the subsequent dictionary learning from the results map of CDL-SL in Figure 4. We can observe that the proposed framework accurately expresses the characteristic of the C-clutter. Specifically, the blue curve represents the C-clutter obtained by dictionary learning. The orange curve represents the current received C-clutter and will be learned the features. The black curve represents the detection target. As you can observe from the Figure 4, the blue curve almost overlaps the orange curve, which confirms that CDL-SL can preciously capture the characteristic of the C-clutter and construct optimal C-clutter that are estimated from the dictionary learning. The C-clutter obtained for dictionary learning is more similar to current real C-clutter echo. The more effective the proposed method is. We apply the same C-clutter data to compare the performance between CDL-SL and dictionary represented optimal filter in the high-frequency surface wave radar system. Obviously, our proposed framework has better performance by comparing the experiment results in Figure 4 and Figure 5. The results obtained by CDROF is shown in Figure 5, and it indicates that it doesn't accurately estimate the C cutter in high-frequency service wave reader system. The main reason may be that the sky wave over the horizon reader system can receive a lot of cutter angle when it is started up for daily operation, but most cutter data contains targets and interference. Irrelevant training samples will seriously affect the performance of the model, thus influences the suppression effect of the algorithm. And the CDROF applies fewer relevant samples which cannot mine rich hidden C-clutter informations. In Section 5, Conclusion. In this paper, we present a C-clutter suppression method for high-frequency service wave reader. The proposed algorithm, named a Cooperative Dictionary Learning and Semi-supervised Learning C-clutter Suppression Framework. Applying enhanced M-training algorithm with different classifiers to obtain vast amounts of the C-clutter data that almost contains no target. This poor C-clutter data is applied for the sparse representative and dictionary learning to capture the characteristics of the C-clutter. Moreover, with the cooperation of online real-time and quasi-real-time, the proposed framework can accurately detect the targets among the C-clutter. To further evaluate the performance of the proposed framework, we also conduct the previous research named Sparse Dictionary Representative Optimal Filter CSDROF on the high-frequency service wave radar system in the same experiment setting. The experiment results effectually prove the superiority of our proposed framework in high-frequency service wave radar system. That's all. Thank you for your attention.